Hey, welcome back to another video from me, Gareth Evans. Now, today we're going to be looking at isotopes, mass number, and atomic mass. Now, if you haven't seen my last video on the inside of an atom, I'd recommend that you go look at that video first. So let's say we have some carbon. Now, carbon is an element, which means that every one of its atoms has the same number of protons as the other atoms of the same element. So wherever we are and wherever we go, a carbon atom will always have the same number of protons. So here we got some carbon, and in there the carbon atoms will always have the same number of protons. We can therefore write out this information in the following format. As you can see, the proton number, so the number of protons, is 6. And conventionally, as we will see in a minute, this is provided with the symbol Z. So the proton number is given the symbol Z. So when writing out an equation in symbol form, you will know that the bottom number, okay, as you can see here, the bottom number is going to be the number of protons. In other words, it denotes the number of protons inside of the atom. So we got this AZX formation, and the number 6 corresponding to the letter Z is the number of protons inside the atom. Okay, so let's look at an equation of uranium decaying into thorium. What is the atomic number of the proton number of uranium? So here's our uranium in the equation. Okay, what do you think it could be? Now, if you remember that our notation is AZX, and we know that the Z corresponds to the proton number, therefore the proton numbers in the uranium must be 92, as that will correspond to the Z there. However, although the proton numbers, so although the number of protons inside the atom will always stay the same, atoms of an element can have a different number of neutrons. Okay, so although our various carbon atoms will always have 6 protons, they won't always have 6 neutrons in the nucleus. Thus, atoms of the same element, therefore having the same number of protons but with a different number of neutrons, are called isotopes. And that's what we're going to be looking at now. For example, carbon-12 on the left and carbon-14 on the right are two isotopes of the element carbon. Now, the atomic number of carbon, as we have just seen, is 6. Which means that both isotopes have 6 protons, and that can be seen in the picture here. So we got these 6 positive protons on the left hand side in carbon-12, and these 6 positive protons in the right hand side in carbon-14. So there's our proton. And however, the number of neutrons in both these isotopes though is different. Okay, so in carbon-12 this only has 6 neutrons, whereas in carbon-14 they have an extra 2 additional neutrons, making 8 neutrons. Now that we know that the bottom number here and here, i.e. the Z, the letter Z in our notation, means protons, what is meant by A on top? What is meant by the notation A? Now this is the combined number of protons and neutrons in the atom, and is called the nucleon number. Okay, so let's write this out. Nucleon number. Excuse my handwriting, but that's the nucleon number, or it's also known as the mass number sometimes too. So we can see, for example, in our carbon-12 that this has 6 protons here, and as this is the combined total of protons and neutrons, we know that there are also 6 neutrons in this atom too. So if 12 is our combined total, and we know there's going to be 6 protons, whatever's remaining must be the neutrons. So 12 minus 6 equals 6. Okay, so take a look at these two isotopes of boron. Boron-10 here and boron-11. Now boron-10 on the left has 5 protons in red and 5 neutrons in blue, whereas boron-11 here has got 5 protons, but it also has 6 neutrons in blue. Now we already know that the mass number is the total number of protons and neutrons. So boron-10 has a mass number of 10, and boron-11 has a mass number of 11, as we know that there are 5 protons and 6 neutrons. Add them together, that makes 11. And here we've got 5 protons and 5 neutrons. Add them together, and that makes 10. Now the mass number is also important because it gives us an idea about how much the atom weighs. This is because one proton or one neutron weighs 1 atomic mass unit, so 1 AMU. Okay, so each of these little blobs, each proton, each neutron weighs about 1 atomic mass unit. So if you have a mass number of 10, such as our boron, 10 here, isotope, then that will weigh about 10 AMU. Okay? Now if you have a mass number of 11, such as boron 11, then that means that our boron 11 isotope will weigh about 11 AMU. These atoms both have electrons, but electrons are so tiny, so our little electrons flying around the outside here, they all have electrons, but they're so tiny, they have such a small amount of mass that we don't even need to worry about the mass of the electrons when we're weighing up stuff to determine how much the entire atom would weigh. So let's just focus in on the atomic mass itself. There are billions and gazillions of boron atoms in the world. Like, there's just loads and loads of them. If we could pick up one at random, let's say I could just, walk down the street and find a boron atom and pick one up. It could be either of these two types. We'd either have a boron 10 atom in my hand or a boron 11 atom. Okay, so it could be a boron 10 atom with 5 protons and 5 neutrons, or a boron 11 atom with 5 protons and 6 neutrons. So borons come in these two versions. Now, the thing is, there is not an equal number of boron 10 and boron 11 atoms. In fact, if we pulled, let's say, 50 boron atoms out at random, I was walking down the street and I picked up a boron atom here and a boron atom there, and I went and got 50 different boron atoms, we'll see that the majority would be boron 11, okay? The majority of them would be boron 11, which I'm indicating with little red circles here. So here we can see the little red circles are our boron 11, whereas only a small minority of the boron atoms that we could pick up at random would be boron 10, indicated in blue here. Now we can also look at this information on a pie chart just to get the point home. You can see that the vast majority of them are boron 11, with only a small amount that's boron 10. And if you crank through the maths here, you'll find that about 20% of boron atoms in the world are boron 10, and 80% of them are boron 11. And this leads us to the idea of atomic mass. Okay, now atomic mass asks us, what is the average mass of a boron atom? Alright, so we've got these two atoms of boron here. We've got boron 10, that weighs 10 AMU, and we've got boron 11, which weighs 11 AMU. And that's what its mass is. But here's the thing, there is only 20% of this guy, so we've got 20% of this guy, and there is 80% of this guy. Okay, so now we're asking, we've got these two types of boron, what is the average mass of the boron atom? Now you might think, this is easy, okay? I know how to take an average. We go, well, this guy weighs, 10 AMU, and we know that this guy weighs, 11 AMU. So let's just, add them up, so 10 plus 11, and divide that by 2, and that would give us 10.5. Right, does that not make sense? But, if you did that, that would be pretty wrong. So I'm just going to get rid of that and tell you the proper way of doing it. Now, that is a way of taking an average, sure, but it isn't the way that will work here. Now, the reason why is because this type of thing added up and divided by 2 assumes that we have the same amount of boron 10 and boron 11, but we know that, so if we had 50% of boron 10 and 50% of boron 11, then we could just do that. We could just add up the mass number of both of them and divide by 2. But we can't do that here because we have different amounts of these two types of atoms. Okay? And we have to come up with a mathematical equation that is a little bit more complex than this and takes into account the different amounts of each of these atoms. So here's how we do it. So we take the fact that there are 20% boron 10 atoms that weigh about 10 AMU each. So 20% times 10 AMU. So we got 10 times 0.2. Okay. And we got to add that to 80% times 11 AMU. So let's add that to 11 times 0.8. Okay. And when we have to do the maths, we have to convert the percentages into decimals. So that's why here we've got this 0.2, because 20% as a decimal is 0.2 and 80% as a decimal is 0.8. That's why we've got 0.2 and 0.8 in this equation. Now completing this equation would give us 10.8 AMU. And this tells us what the average weight of a boron atom is, taking into account that only 20% of the boron atoms are boron 10 and 80% of the boron atoms are boron 11. Now check this out. If we look at the periodic table and we find boron, which is just over here, okay, you will see underneath it on most periodic tables there is a little number underneath, and here we have 10.811. So on every element of the periodic table, the number at the bottom is the atomic mass, telling you what the average weight of one of those atoms is, and this is exactly what we have just worked out together. Hopefully that explains isotopes and all those pesky little numbers that you may find when discussing atoms and isotopes in physics. Now, if you have any questions at all, please leave a comment below and I will get straight back to you. Thank you very much for watching.